Now let's do an example. We have a function and we need to find intervals of continuity of this function. What we can easily state, we can recognize that f of x is a polynomial. And as a polynomial, it's continuous on its domain. What is the domain of polynomial? Domain is all real numbers. Long story short, the intervals of continuity of this function is a single interval between negative infinity and positive infinity. Another example, we need to find intervals of continuity of this function. And what kind of function is it? It is a rational function. And as a rational function, it is continuous on its domain. Now, to find the domain of this function, we need to identify the points where denominator is 0 and exclude those from the domain. So we'll try to factor the denominator, and it looks like x plus 2 multiplied by x plus 5 is the factorization. So we identify that the denominator is 0 at a couple of points. For domain of f of x, we set x plus 2 times x plus 5 equal to 0. So we find that x is either negative 2 or negative 5. Those are the points we want to exclude. To help us come up with the intervals of continuity, we'll make a sketch. So here is point negative 5 we'd like to exclude, there is point negative 2 would like to exclude, and everything except for those 2 points will constitute intervals of continuity. We get negative infinity up to negative 5, together with negative 5, negative 2, joined with negative 2, positive infinity. All the endpoints of such intervals are excluded. One more example, we want to find intervals of continuity of cube root of 12 minus x to the 4th. Again, so this function is continuous on its domain. Because it's a cube root. Now, what's the domain of cube root? Well, cube root works for both positive and negative numbers, so the domain of f of x is all real numbers. Then that's where this function is continuous. On to the next example. we want to find intervals of continuity of this function, f of x being square root of 11 minus 5x. That's again a root of some expression, so this function will be continuous on its domain. What's the domain of f of x? You see, it's a square root, so square root works only for positive or maybe 0, only for positive numbers or maybe 0. So for the domain, of f of x, we set the expression instead of square root 11 minus 5x being greater or equal to 0, and solve that. And as soon as we solve that inequality, that will be exactly the domain of the function. So we move 5x on the other side and get 11 being greater or equal than 5x, and then divide by 5 both sides. We have that x is less or equal to 11 over 5. In interval notation, that's the same as interval from negative infinity up to 11 over 5. With a square bracket, because we still include 11 over 5. Now, if a function is not continuous at a point, but the limit as x approaches c of the function exists, such a point is usually called, such a discontinuity is usually called a removable discontinuity. Otherwise, such any other discontinuity is called non-removable. So the nice feature of removable discontinuity is that if it is possible to assign a new value to the function at x equals c, so that the function becomes continuous at that point. Let's have a look on some of the examples of discontinuities. The very first example on the left is a removable discontinuity. Because the graph approaches the same height from the both sides of x equals c, so the limit will exist, but the function is not equal to the value of the limit. So what we can do, we can redefine the function. So we can cross out this value and take the marker and fill in that point at x equals c to make it precisely a one-piece continuous function. Now, the other two functions are not having removable discontinuity, because this function in the middle doesn't even have a limit as x approaches c, and the function to the right also doesn't have a limit as x approaches c. The graph doesn't approach the same height from both sides of x equals c, on this graph and on this graph in the middle. Now let's do an example on investigation of discontinuities. So we have this function f of x. It's a rational function. Okay, we have this function f of x. F of x is rational. So it will be continuous on its domain. For the domain, we set x squared minus 16 equals 0. And we get that x squared is equal to 16, so x is equal to positive or negative 4. So if we exclude those 2 points, that will be exactly the domain of the function. and those are intervals of continuity. And now what we can investigate if any of those two discontinuities is a removable discontinuity. So for that, let me factor out both numerator and denominator. Looks like the numerator could be factored into x minus 4 times x plus 2. So what we need to investigate if the limit as x approaches -4 of this function exists. Well, even though we can cancel x minus 4, we still get x plus 2 divided by x plus 4. And if we try to do direct substitution, we pretty much get an expression like -2 divided by 0. And that's pretty much the indication that such a limit doesn't exist. And if limit t doesn't exist, such discontinuity is non-removable. For another limit, as x approaches +4, of x minus 4 times x plus 2 divided by x minus 4 times x plus 4, we get something useful. So that becomes 6 divided by 8, which simplifies into 3/4. So the limit as x approaches 4 exists, and that is a removable discontinuity. So x equals 4 is a removable discontinuity. And x equals -4 is not.